Hello, this is Trevor Holmes, along with Travis Stockwell and Stephen Ish. We're going to be presenting a case study on evaluating the legacy to cloud migration horseshoe. The legacy to cloud migration horseshoe is proposed in a framework for architecture driven migration of legacy systems to cloud enabled software by Akesh Ahmed and Muhammad Ali Babar. They also had two or three previous works that we will be incorporating into the framework. This framework fits the ISO IEC 14764's framework for software maintenance and more specifically implements a migration phase, which flows into the implementation phase of the system for the new cloud environment. Once the systems are migrated, the legacy system will be transitioned to retirement phase of the ISO IEC 14764 framework. The legacy to horseshoe migration, as you can see in this process, is iterative. So what we're going to be doing is just migrating or describing the migration process for one component for Optum's transaction integrity software from a legacy system to their cloud environment. And they kind of walk through the steps. They closely follows this model. It's all kind of the same model, just different pictures and some slight different vocabularies. And then eventually, not that has not happened yet, but eventually Optum will retire their legacy system. This is the diagram of the overall process. You see the horseshoe. But basically, we start process one is like any good project, you do a process or a planning. You do feasibility studies, case studies, requirements analysis with the stakeholders. You have to examine the cloud providers and determine which ones you're going to use. Then you develop an actual migration plan. Goes to step two. And we're going to do some re-engineering. We're starting from bottom up. We're going to go from reverse engineering. We're going to go from legacy code and then identify the actual architecture of the legacy code. In our case, it's good we have three of the original developers, so this isn't technically legacy software yet, but it's still a migration from an older platform to a newer platform. So it still should be a good case study. But since we have so we have several of the original developers, some of the semi-automated processes that were the goals of some of the framework processes, we will know exactly what the architecture was from the original from the pre-migration, so it's very helpful. And then we will go over some of the techniques, and we will use them to describe how a semi-automated process could work in this. And then once we have the original architecture laid out in front of us, we'll have process three is transformation. So we will go from that architecture to a cloud based architecture, and then four. We'll do the changes then in step three, and then four will actually implement. It was implementation. So we'll go forward engineering and actually then go from top down and then produce the cloud-enabled source code. Process one is the architecture migration planning. Stephen and Travis worked together closely on this to generate the costs, benefits analysis, economic, technical feasibility, the project plan and scheduling, and then they compared the private, and then Stephen really compared the private versus public and gave us our motivational organizational value or measurable organizational value, and then also did our scoring matrix to decide which platform that Optum was going to use which cloud platform Optum was going to use. Before we could really analyze how we're going to migrate it, we needed to learn what the application actually did, just to have a familiarity with it. So Travis is and was one of the original developers of the legacy application, and so he's going to go into more detail and breakdown of the legacy later on once we get to the actual reverse engineering of it. but just in general, there's a simple diagram here. What goes on? Each client requires has their own single server. In most cases, there are some larger ones that have load balanced web farms, but in most cases, it's a single server running all the instances and the applications of MySQL, a web server, and then there's their middleware and business logic. The average case database is about 500 gig. There's 10 million claims per month, and the uh, the number of reports and stuff that are generated are not stored on the actual server because there's so many. It is a case by case per customer choice, and Travis will go into this too, and it's one of the reasons why they wanted to. But it was one of the reasons why they wanted to switch to the cloud. The saving of the reports and because each customer is different, they all want something different, so they can customize their own outputs now in the newer environment. Whereas before it was kind of they had to build them, and then it was all that stuff was stored. Where now it's just on demand, and so just the source data is stored versus all the data that's generated. In general, the some of the advantages of cloud architecture versus the legacy or single server type component based architecture is there's the elasticity of each component. Um, it can scale horizontally. It can scale vertically, but more the real advantage is scale horizontally. Um, and then each component can scale too, not just the whole application just duplicates. So if there's only certain areas of your app that is really used heavily, you can just scale that versus the whole thing. That's kind of really what they were looking um, for one of the major reasons of transfer, and also switching their database from MySQL to a NoSQL or not only SQL data store, which allows them to scale both regionally and just locally horizontally. So Optum has so this is our weighted scoring matrix after all of the studies and working with Travis and Stephen really did a large share of this. So Optum has their own private um, cloud infrastructure that is a Red Hat OpenShift architecture, and Stephen's internal division will still be charged by it won't be green dollars, but it'll be Optum bucks if you want to use that term. So there is a cost to that to their group. So if you look at this, we kind of looked at every option that they had out there, and then discussing the choices with the stakeholders there at Optum. We kind of used the legacy as a baseline for most things, and then you can see the weights and the scoring. Um, so as these things can be, they wanted to use their internal private cloud, so they can change and weight things separately. But anyway, they're so they as you can see, they've gone with their internal OpenShift cloud. Interesting though that, and we've been talking with Travis, some other stakeholders. They are looking to transition portions of this to the public cloud. When they initially were looking at this, most or at the time, I believe they weren't HIPAA compliant, but now they are. Um, and I think their security probably is better than what they are internally using for security. And another goal, or one of the other goals for moving to the cloud, was to offer this service outside of Optum, as most of their customers are internal. But this would be a useful tool, or the transaction integrity would be a useful tool for external customers and also increase their business. So once we had our migration plan set up, we go to process two, and migration plan is the input for process two. So we consolidate all the code, um, and then we use a process there, which I'll describe, and then we do modeling, and then we extract the architecture. So we're starting from the bottom, we're working our way up to extract the legacy architecture, and not just identify kind of what it is, but we have to identify every component in a reusable vocabulary across multiple technologies to allow for our migration from legacy to cloud. This technique was described in previous papers that these gentlemen produced, and they're linked in the source in our paper. But it was very interesting and used a lot of graphing, which just seems to be the most useful way to identify architectures. We've looked for several or industry standard architectural description languages, which really aren't there. It almost seems like it's case by case. You kind of define your own description language, which these attribute graphs and then attribute type graphs are kind of your own architecture descriptor language for either your particular company or an industry that would kind of work together. Um, and it was very interesting and helpful to kind of to see this at a higher level than I've been used to, and than Travis or Steven are used to. We've been in our experience that we've been more of you get down you can kind of get bogged down in the details in the legacy and in the actual just programming. So the higher level view really helps you kind of when you're programming too, kind of consider what you're doing overall and the decisions you make when you're coding. So activity one is a consolidation of the legacy source code. Now Optim has all their source code in Git, and that doesn't. It's kind of vague, and this framework is very flexible. I don't want to say vague. It's flexible, and it allows you to do. It gives you a goal of what each activity or process is supposed to do. Allows you to decide how you want to do it. Um, in this case, we kind of knew we had the actual developers for the legacy code, so we didn't have a set tool to do this. But in their research, they have used a paper called "Recovering Software Architecture from Multiple Source Code Analyses," and that's also linked in the sources. What it does, it describes using the MANSART, which is the Mitri Software Architecture Recovery Tool, and it analyzes software. It's more of a static analyzer, and it doesn't do dynamic analysis, but it analyzes a source code and it generates. I'm going to call it a vocabulary. They call it an analysis module interfaces (AMIs) for the source code from every aspect of the thing, no matter what language. That's so that you can use any tool you want as long as you get some sort of common vocabulary to describe how these components interface. So to produce these analysis module interfaces, these AMIs. So we kind of used, you can do it automatically or manually. We did it manually with Travis's help to identify each component and then what all the different parts of the components and how they work together into a language, a vocabulary. Once we have that, our the application description done, we can then we can then extract patterns and styles from the architecture or that component description or using the AMIs. And kind of this is a pretty common architecture. It's a view MVC view model control, and those are the components and kind of where they are in that model or that architectural pattern. Once we have this, then we need to check make sure it still meets the constraints. Activity two of process two is the pattern and style extraction. Using the AMI language or analysis modules to using that vocabulary to identify specific endpoints, connectors, components, interfaces. As I mentioned before, because of our time constraint here on this project, we're just going to be using migrating or describing the migration for the controller portion of the component. So I'll just the red box around the controller, and we're going to expand that. And Travis is going to introduce the process and in general go over the actual legacy code and kind of exactly what it does.
Let's start with this pre-cloud slide. You can tell here, we're looking at the legend up here on the left. There are the endpoints that are colored purple, interfaces that are beige, migrated, merged, and legacy components, and some removed components and external components and connectors. Let's talk for just a minute about how what this system does. I think that might be helpful. The entire system is designed to take in EDI, electronic data interchange, for the healthcare industry. It takes these formatted documents and it analyzes them against the requirements of the HIPAA regulations regarding these documents for syntactical correctness as well as semantic value, and there's some business logic in there as well. That's what the entire system is designed to do. It can be configured as part of the process of analyzing these documents to produce reports regarding it. And these can be user consumable reports that we'll see a little later. They can also be machine readable reports to let the submitter, which is usually something like a hospital or a doctor, let the submitter know that the document was invalid in one way or another, or valid and accepted. And then the system will record the information extracted from the document into a MySQL database for searching and analytics later on. So the front door for this, that you'll see on the far left, is the HTTP API, and that consists both of something that a machine could interact with, as well as some HTML for a user to submit these HIPAA documents manually as part of their testing or debugging and so forth. When a user uploads a file, the file is put onto the disk, and you can see that way over on the far left. Far right. There's a file system component. It also gets an entry in the database to give the file an identification. So then back to the left, there's a component that's been labeled controller.pl. And this guy, he's the brains of this operation. He is monitoring the MySQL database for new documents that have shown up. He sees a new entry for a new document. He pulls it, pulls that entry from the database and forks a process and starts working on it. He does that by sending a request to the analyzer component, which you can see closer to the top. It's up in the top right. He sends a request to this analyzer component telling him, hey, there's a file on disk. I want you to analyze it and send me everything that you can glean from it. And that request is made with the HTTP protocol. It's a GET, and what comes back from the GET in the body of the HTTP response is TDV. Those are tab delimited values that are records that explain all the things that were discovered in the document. Anomalies, things that are in error, and even things that are required for some of the affirmative acknowledgments that can go back to the user. And that is all sent back to that controller.pl component. He has, right after he has started his request, he has started all of the little, we'll call them side effects, that want to happen as a result of analyzing this file. And you'll see that kind of in the middle of the document in a lot of blue, and there's a yellow and some red and green. All of those little boxes are the little side effects, and they are producing human readable reports. They're producing machine readable. At the top, you can see a lot of the machine readable, like the 277 document, the 824 document. There's a 277 acknowledgement. There's a 997, which is a very simple response, a 999, which is more complex. One of the other things that happens as a result of completion of the analysis of a document is that it will need to be torn to pieces. This document will be split up into pieces and routed to different destinations. And that can be as simple as good claims and bad claims, but it can be more complex, where you might have high dollar claims or ambulance claims or claims that need review before submittal and so forth. You'll see also that there's a TIFF image generation. That thing, it's in red because it goes away. We'll see that on the next slide. There's a history component that loads all of that information up into the MySQL database to be mined for information. There's even a transformer, and then the split join. You can see the split join component at the bottom in the middle. That's the thing that pulls the file apart and puts it into pieces. And that's all sent up to a router that will send things to the different places on the file system or even externally.
Activity 4 is the legacy architecture consistency conformance. So the architecture constraints are only the view layer can depend on components provided by the HTTP API. Only data access objects from the model layer can depend on database services. The view layer can only depend on services provided by itself and by the controller layer. For example, to decouple data presentation from data access, view components can't access model components directly. Domain objects must not depend on the DAO, controller, and view types, and the DAO classes can only depend on domain objects. On other model classes allowed to use database services. Using those constraints, we constructed a dependency structure matrix to verify the consistency of architecture consistency conformance. And as you can see here, you can see that wherever there's a one, that's where the dependencies are in the architecture, and it does meet those constraints. Process 3 is the architecture transformation. So our input is the legacy architecture from process 2. We then take the architectural model and transform it using the patterns that we find into the cloud service architecture model. And then our output is a transformed architecture that we can then use to generate our architectural source code. Process 3 is the activity 1 is the architecture change implementation. Now we use the previous work by this group by Akash Ahmad called graph-based pattern identification from architectural change logs. Now it provides a process to go through the architectural change logs and identify patterns. These change logs are basically made up of atomic, they call them specifically atomic change operations that are knitted together into composite change operations to perform add functions, remove functions, and modify functions on the components. And so in this slide, there's two sequences here, sequence 1 and sequence 7. We made all the sequences and all the atomic change instructions are in a spreadsheet, and we'll submit that also for you to review. I did these two components these two sequences because first one's a remove and the second one is an add, um, or a migration of a component. And that's repeated several times. Now, our our case study is for a very small component. It would work after going through all this. It would work very well on a much larger, more complex component that has a very strict um, change management system. So all these changes are done ahead of time. So you don't have to go back, or all these changes are logged or somewhere, so that you don't have to go back and reproduce this. You just have to mine the data. And I know they're out there. I've not had that. I've not been in an environment where that has that strict of a change management system. Um, and I believe Stephen is in an environment, and it might be more. It might work better for the more embedded software because it's not so fast moving. In the DevOps environment, I don't know how you would even operate a DevOps environment without having a very strict change management process because you're constantly redeveloping and producing new models. So if you look at this, anyway, back to the what we're doing here are these atomic changes. Instructions and sequences. So the first sequence, like the first line would read, in sequence one, change instruction one, we're removing the history report endpoint from the MySQL-history connection. And then then we would say the second line is sequence one, change instruction two, we modified the MySQL history connector in the controller configuration. Now that would in our later on the NID is a node ID for our attribute graph, and so that would be the first node in our change process. That would then be linked to the second one via an edge, which I have an edge ID, and I'll show you that. It's coming up in the next slide. Okay, in this slide, this is our first introduction to these attribute graphs and attribute type graphs. Now, this is for that first sequence that I showed you in the previous slide. So our attribute type graph, we take our attribute graph is typed using the attribute type graph. This is to me, and I could be wrong on this. This is more of a architecture description language, or it could be a change management description language. However you want to look at it, basically it produces a graph of your change instructions, which is great because then you can use the graphing graph mining processes there's several of them to go about semi-automatically generating or modifying or creating source code for migration. Maybe not so much the internal logic, but at least for sure your structures, your classes, connectors, and all that can all be created up beforehand. All you would have to add then would be the code to actually perform the logic, which should hopefully be fairly easy as long as you're not changing that and you're just lifting and shifting from your existing platform to the new cloud platform. So as you can see, this says the remove. I'll go over the add later, but you can see so that first node ID produces the mod. It is a modification on the process file connector. Um, it removes an endpoint. We're going to remove the history endpoint, and that connector connects the controller.pl and the history.pl. And once that's done, it goes over to the next. The node has an edge that points to the next modification, which we're going to remove another endpoint. We're going to remove the history report from the MySQL history connector, and that connector connects history.pl and the MySQL history. Then finally, we remove the whole component once those endpoints are done, and in that we have to remove two interfaces, the history interface and the history report interface from the component, and then we can remove the component. Okay, this is the composite sequence of change operations we're adding a component. The first change operation we're going to add the submitter report pod. It has one interface, the submitter report pod interface, and then once that's done, we go to we're adding an endpoint to connect the components. So we're going to add the we're going to modify the task connector. It's already been there before. It was in a previous thing. We didn't show that, but the task connector has been created. We're going to add an endpoint to it called submitter report pod, and it connects the workflow component and the submitter report pod component. We then we're going to remove an endpoint. We're going to remove the submitter report endpoint from the process file component from the legacy system. And then we're going to then remove another endpoint from the reports connection in the legacy system. The endpoint is the X12 submitter report. And then once that's done, we're going to then remove the submitter report component from the legacy system. And we also have to remove two interfaces from there first, which you'll see the submitter report and the X12 submitter report interface. So then once all those sequences are done, we end up with the changed architecture model. And then we generated this diagram and also the previous one that had the whole process of what we were showing you. It's not required. It just made it easier for us to visualize what we were actually doing. And then Travis is going to go over this portion of it.
And you'll see a number of things have changed here. So starting from the left, there is a very simple API, and it's just HTTP, and that's how the user interacts. That part didn't change quite so much, but he accepts the document, and then he puts that thing into a queuing system. You'll notice that there's a RabbitMQ component on the far right. That's a new thing. It's one of the kind of the cool things we have about the cloud is that it's actually external to the OpenShift system that's being used. It's a service that you can just plug in. That's really convenient. The same goes for Object Store. Same goes for MongoDB. Those are things that are external and they just work all the time. They're up all the time. They're fully redundant. It's one of the cool things about being in the cloud. Well, once that thing goes into the RabbitMQ, it can queue up forever, which is nice. You can have a whole bunch of them, and then as quickly as we can handle, as quickly as we can scale, as quickly as the system can manage it, the workflow component, which is kind of it's the new brains of the operation. It behaves differently, but it's the new brains. It's that kind of orangey thing in the middle. It'll pull that request off of the RabbitMQ, and it will do, in some ways, the very same thing. It will send a request to the analyzer, which has now become it's a Docker image, and it's running in its own pod, and it can auto-scale as much or as little as we need. And it, just like before, just like in the pre-cloud situation, it sends back TDV, and it's actually the same set of data. It comes right back. Only now this data gets thrown directly into MongoDB, and then everything kind of stops right there. And what happens now is that the user makes additional requests for the things that they actually need. So in the pre-cloud, you submitted a document to a pre-configured set of side effects, things that you want to happen every time you submit in this manner. But here in the cloud, we do it a little differently. We do everything on demand because it can be done quickly, and we also know that users very rarely want the same things every time, and that there's a lot of waste if we are doing all things all the time. So we make them ask for things. So at that point, the user can make another request to the API, and will ask for, um, I'd like a submitter report or a velocity report, or I'd like the file to be transformed or split into pieces according to these rules and so forth. And those requests get forwarded via HTTP um, to these different little, I don't know what you call this color, teal components here. The request is sent there along with the file and some instructions. So it's important to know in this architecture that all of these teal components act independently. They they don't know how the files are being stored. They don't know anything other than their little job. And they don't know how to talk to Mongo or RabbitMQ or anything like that. They just wait for requests. They scale perfectly, and it works really great. And that's how the post-cloud migration works.
Final process is architecture-based development. So our income process income is going to be the cloud-enabled architecture, and then we identify our cloud service architecture, and then we match the patterns that we're going to be using in the cloud architecture, and then we generate the code. And then our outsource is the source code. So once we have the architecture done, we need to identify some of the patterns then in the architecture. So what we've looked at and also spoken with the stakeholders. What it does have is the queue-centric workflow pattern. Excuse me, and that's used. You can see when they use the rabbit the component. That's all it does is it queues up tasks. If they're not initially, it goes to the queue and it waits until there's resources, and then the workflow pod grabs whatever the next task is and goes to work on it. They also, in that regard, they're horizontally scaling. So it does that in that compute pattern. Basically, any portion of that you see on that diagram can be scaled horizontally. That means it can just duplicate its effort because all those components are decoupled. They're not dependent on each other. They have great elasticity. There's no state in these, which was great. I think they were designed, or the legacy was also designed stateless and some and fairly semi decoupled already. So this was a fairly easy migration. But they also do the OpenShift architecture also has auto scaling. So the queue and the auto scaling kind of go hand in hand. And the horizontal scaling, they all kind of go hand in hand so that it'll ramp up and deramp. It's one of the main benefits of having a cloud. You're not paying for all this capacity all the time. You're just paying for when it's needed. And then they also do take advantage. You can't really see this in our based on our patterns, but they do have multi-site deployment, and that's just from us talking to the stakeholders there. There are two separate geographically located data centers right now, and if they do go to the public cloud for certain portions of this, which they're talking about doing in the future, then they of course will then be geographically deployed to decrease latency for their customers. So this is our cloud architecture after our transformation. Um, this is our simplified version of it. I'll show you the next slide. I'll show you the actual architecture that Optum uses for the entire application, not just our controller component.